our last case, so there's case 1, here's case 2. Our last case is when our discriminant b squared minus 4 times a times c is less than 0. That gives us a negative number, doesn't it? Gives us a negative number. And what happens is, this means our solution, so it's an S, it looks like a C, but it's an S. Solution is, how about this? Solution is a complex number. Is a complex number. Oh, wait a minute. Oh, and remember, complex roots travel in pairs. So if I knew that one of my answers was maybe a plus I omega, what would my other solution have to be? Right, and what did we call a minus I omega? The complex conjugate, right? Because remember, you can use conjugates when you're trying to rationalize fractions. So it's also a plus I omega and a minus omega. What is this? This I omega, what does it introduce to the solution, though? It introduces circular motion. It introduces sine and cosine into the problem. So this is circular or harmonic motion. Okay, so you get circular motion. Meanwhile, you have something trying to go in a circle, but what does this A do? Exactly right. This is the decay factor. Or the decay, I'm going to write it this way. It could be decay if it's negative, decay, or it would be a growth factor if it's positive. So the A is the decay or the growth. If you looked at it in a circular picture, it would be a spiral. If you looked at it over time, what happens is, this is clearly a blue graph. So if you look at it over time, you have some starting value. Who knows where it is? Maybe it's here. And what's going to happen is, over time, it's going to want to start oscillating by sine and cosine. And remember, you can just make that into one cosine. But then what happens is that oscillation gets brought in under control because of the decay. If A is positive, your oscillations are going to go. Point that up. And you can make that noise.
So we have to pay A less than 0.
Yes.
Growth of A greater than 0. And we just have a constant that A is 0.
Oh, that's a good question. If A is 0, what would our solution be? Okay, just here. Erase it. So you put I omega in there, wouldn't you? This would be E I omega plus C2 E minus I omega. These are perfect sines and cosines. So you can collect them, regroup them, and what you found, and let's write that, that's a good question. What we found is our null solution would be of the form some C1, where that's a capital C1. It's a collection of C1 and C2 cosine omega t plus, then we call it capital C2 sine. Can you guys read that blue? It's kind of dying, huh? And you remember what capital C2 was? It was a collection if I recall, I think I remember the order. This C1 was C1 plus C2, and capital C2 is C1I minus C2I. That's their signs. Okay. And if you only have sines and cosines, what do you have? You have circular motion. Also, we need a name for this. We need a name. What did we call that? We need a name. Call it something. Call it Joe. We actually have a different. Underdamped, right. Underdamped. This is an under. Oh, I needed that. Can you guys see the red in the back? You like Joe better. Underdamped. Johnny, is that clear from back where you are? You're back there? Okay. All right. All right. Yes, and what was a real life example of an underdamped system? Yes, and what causes it to keep bouncing?
Shock.
Right, the shock absorbers are shot. Yeah, so if you took them out completely, and that's, remember the test, is you go ahead and jump on it, and you hop off, and if the car keeps bouncing, that's an underdamped system. If the car quickly stops, then you have a critically or overdamped system. That's more what you want. Okay.
So is underdamped showing that like at the start it will go really high and then go down and then start slowing down bounces?
Yeah, that's right. So like when I jumped on the car, my system probably would have started in this position. Maybe this is the car's bumper. Right there. Chunk of the car. So when you jump on the car's bumper, initially the bumper is going to drop. It's going to go in. I'm going to just make the scale exaggerate, but the bumper is going to drop. The spring's going to push it back up, but there's a little life in the shock absorber, so it's going to pull it back down, but the spring wants to push back up, and the shock absorber pulls it down until finally it's from that. So in that case, your initial conditions would be where you probably your initial condition actually wouldn't be there. It'd be right there if you jumped on it. Yeah.
Are these all fluid acids negative?
Yes, all of these imply. A is negative. It's a decay factor, and then yeah, this is negative. Because if it's positive, the system's just going to go as out of control.
So we would call it something different. It's
Unstable. Yep, it's unstable.
So the wire promoter describes the motion of this like device as a function of time. Like, okay, if you're showing that the spring is pushed down, and then it's pushing itself back up, then come back down, and slowly
Yeah.
gapping over time.
Yeah, let me explain that. This actually came up the other day, recently. So one of you were asking me this. So let's think about the car. And you land on that car bumper, you're determined that, heck, maybe the shocks work fine, but you're going to hit it so hard that you're going to wear the shocks out in one good stop, right? Does the car go anywhere? No, it stays right there. I mean, hopefully emergency brakes on, it's not on a hill or something. I mean, but when you stomp on that car, and if you were to just stand there and you were to watch the car does this. That's it. That's all it does, doesn't it? You didn't see, the car didn't move along. But what happened is this is really hard for us to study. So what we do is we take frame by frame shots. So what we do is this. Is we hop on the car, and it goes down to here. And then what we do is we track it. Like, if you're talking about a car, you're probably talking like hundreds of a second. So what happens then is this little dot moves to here, but meanwhile, 100th of a second is passed. And it's a continuous motion, so we're a little bit closer. Another 100th of a second has passed, and the car has risen a little bit more. A couple hundredths more passed, and the car is up to its initial resting height. And so we would say that our graph is now at our initial resting height. But the shock absorber is kind of shot, so the spring pushes hard. The spring pushes it back up to here. And the graph goes back up. And remember, each time a unit of time is passing, those units are here. So here's time, it goes up a little bit. Here's another increment of time, time passes, time passes. So it's, if you take this motion and then you stretch it out over time, is how you can see it. And one more thought on that is, again, back to cars. And cars in unit circles, like I think most of us have learned our trig based on the unit circle. Something going round and round and round. And like, if you look at the, there's a big wheel, the harmonic balancer, is that the wheel on the front of the car? The harmonic balance, yes, that's it. I'll give you some help with that. If you just sit there and you turn the car on, all that the engine on, all that it does is just keep going in circles. And that's the unit circle that we've spent, so that you probably spent a lot of time learning. But if you want to keep track of the unit circle over time, say you want to talk about cosine, then what you're doing is you're mapping that travel over time. It starts at 1, and then it continues on. It continues to start heading back down to 0, but some unit of time has passed. In this case, we would say pi over 4 units of time has passed. But then if you sit there and you stare at it for another pi over 4 units of time, you're at the bottom of the circle, but if you plot that with respect to time, now you're at, oh goodness, pi over 2. And so if you track this with respect to time, you create a cosine curve. This is circular motion. This is harmonic motion. Yeah. It's really about a point of reference, some way of tracking. Does that help?
Now that's where this is the y function t. That means its velocity is greatest right across 0. It's slowing down until it reaches its slowest point.
Right.
0
Slow down.
comes back down as its largest magnitude of velocity at 0 again, because that's slowing it down again.
Yeah, that's right. That's right. Okay. Let me see. I gotta remember what. Guys, have some questions. Oh, I do remember. I remember what I wanted to do. We're going to look at now. So, in all of these things, especially like jumping on cars, when you jump on a car, think about actually jumping on the back of a car is probably I think the most realistic example. Like you could draw a pendulum, or you could draw a spring, but a car is a big spring-loaded system. When you jump on the car, there's an instantaneous force applied to that car. It's not over a period of time. You are just landing on it, bang, you're off the car, because you don't want to sit on it, right, because you get thrown off. What function represented an instantaneous impulse of force? The delta function, right? That's like the most natural way to describe something. So what we want to do is we're going to find what's called the fundamental solution. And the fundamental solution says, what happens if you add instantaneous force to the system? So let's do that. So let's, I don't know, it might take more than this bit of the board, but we'll see, we'll get started. So we're gonna find the fundamental solution. Fundamental solution. And fundamental solution. Let me just put some words down here so when you go home, you're like, okay, wait, what was he talking about? I can't remember, I just kept jumping on the back of a car. So, the fundamental solution describes, that's goodness, I don't know why I keep doing that. Describes when instantaneous force is applied to a system. I.e., the delta function. Delta, I'll put delta of t, that's what it is, just so everyone's clear. All of our examples are about time. Delta function. Yeah, I'll just write that in So let's think about it. So I'm going to write my solution as y, well, I'll write it t, but y of t is equal to, let's just start with what we know, c1 e s1 t plus c2 e s2 of t. Actually, don't write that, stop. You have to be more creative. Sorry. I just had a moment of redirection. Let's do this. So, solve. I should tell you what we're up to, not what the solution is. Solve. Solve. AY double prime plus BY prime plus CY equals delta of T.